propagation delay, they are equal to each other. So the transition, upward transition and downward transition will take place exactly at equal time. And then we also explain the low to high propagation delay. This is the time involved when output is getting charged from low to high value, making a transition from binary 0 to binary 1. So the circuit that will be involved in low to high transition will be this on resistance of PMOS and this load capacitance. These two circuit parameters will determine low to high propagation delay. Similarly, when the circuit is making high to low transition, we are making a binary 1 to binary 0 transition. So it is discharging, and discharging must be down to the ground. So this NMOS transistor will be on. So the timing for high to low transition or that propagation delay will be determined by this on resistance of NMOS and load capacitance. So it's a function of RMCL. So if we just look at these two equations, this is a function of RPCL, this is a function of RNCL. So if we want to make the logic gate symmetrical, CL is common on both sides. All we have to do, we have to play with the sizes of the transistor here and here so that RP becomes equal to RN, then the logic gate will be symmetrical. Now let us see how can we do a general estimation or derive some simple equation to calculate propagation delay. Let us consider a situation when at time t0, we have an ideal input. Just for simplicity, no input is ideal, because what is the difference between ideal input and practical input? An ideal input signal, when it is rising, it will rise from 0 to VDD instantaneously. It's like a step signal, perpendicular signal. An ideal signal, when it lowering from VDD to 0, it will drop down instantaneously with 0 time. But a practical input signal will be like this. It will take some time to slowly go up, and a practical signal, it will be like this when it is going down, right? But for simplicity, let us assume that we have applied an ideal input signal to this inverter. That ideal input signal we input switches from 0 to VDD at time t0, that is, it is going up. Perpendicularly, it's going up 0 to VDD in 0 time at time t0. So as a consequence, what will happen? NMOS transistor will be on because input is high, PMOS will be off. So the circuit that we will have, in this case, CL will be discharging through RN. But let us assume that before we applied that input signal, the output at time t0, it was holding a high output. So at time t0, it was holding a high output at Vout. So Vout will be equal to VDD, high output. So now for NMOS transistor, we know that the output voltage for a CMOS inverter, the output voltage is exactly equal to the drain source voltage, right? Because the output is connected to the drain terminal of NMOS, and the other terminal is source terminal is connected to ground. So the drain source voltage of an NMOS transistor is actually, in an inverter, is actually the output voltage of the inverter. So Vout is drain source voltage of the NMOS, which is VDD at time t0. So now, at time t0, we applied an ideal input signal, high input, which moves from 0 to VDD. So at time t0, VGS of N will be VDD, VDS of N is also equal to VDD. So both input and output, VGS and VDS, if they are equal to VDD, the transistor will be in saturation. Why? Saturation condition is, on one side we write VDS, On the other side, we write VGS minus VTN. Let's put an N here and so if this one is at time t0 VDD, if this one at time t0 is VDD, and which one is greater? This side is greater, so it is in saturation. Earlier today, one of your friends asked me, why at VM, so let me take a little bit detour. Why at VM, switching threshold voltage at this point, NMOS and PMOS both are in saturation, right? So the answer is, what is VM? VM is when input becomes equal to output. In this voltage transfer characteristics, while input is increasing, output is decreasing. At one point they cross each other, where input becomes equal to output, that's where called VM. For an inverter, this Vin is what? VGS of N. This Vout is what? VDS of N. If we put this, so now here it is VM, here it is VM minus VTN. So which one will be greater? This one will be greater, so NMOS is in saturation. For PMOS, at VM, but in general, in case of an inverter, VSD of P and VSD of P in an inverter, it is what? It is VDD minus Vout, it is VDD minus VIN. We are relating the individual transistor voltage with the inverter voltage. So at VM, it is what? It is VDD minus VM. At VM, it will be VDD minus VM, because at VM, input and output equal. So SD of P is VDD minus VM. SD of P is VDD minus VM. So for PMOS also, we have to write on one side SD of P, on the other side SD of P minus VTP. So at VM, this is VDD minus VM, this is VDD minus VM, and there is a minus VTP. So which one is greater? This side is greater at VM, so both will be in saturation region. So you can test for every point VIL, VIH to find their linear condition. So now in this case, NMOS is in saturation because our input and output, gate voltage and source voltage both are equal. Now if you subtract VTN from VGS, this side VDS, that condition, so it is in saturation. On the other hand, as it starts discharging, when NMOS is with a high input, CL, the capacitance, will be discharging to the ground. That means the output voltage will be going down. Initially it was VDD, gradually will be going down. At one point, output will reach VDD minus VTN. At that point, NMOS will enter into linear region of operation. So, let's say initially, as it starts discharging, initially the current, the discharging current for NMOS will remain constant. But at one point, when output reaches this point, VDD minus VTN, the current will no longer remain saturated or constant, the current will go down gradually. But throughout the entire process, from the beginning end, output will be continuously discharging. Output will continue to discharge until it reaches zero. We get a final ideal zero output, right? But now let us concentrate on this region. Initially the current is constant because initially it was in saturation region. At Vout equal to VDS equal to VDD minus VTN, NMOS will leave the saturation region, enter into linear region, and then current gradually decrease. Current gradually decrease, but in the process, it will continuously discharge the output voltage across the capacitance, it will go down. Now, at one point, output will reach half VDD, right? Initially, output was what? Initially, output at time t0, it was equal to VDD. VDD, it is discharging. At one point, it will reach VDD minus VTN. And further down the road, at one point, it will reach half VDD, right? 50% point of the output. So now, propagation delay is by definition, propagation delay, in this case we are doing TP high to low. TP high to low is the time for 50% point of the V out minus the time when 50% point of the input. So all this we are doing to calculate this high to low. At the beginning, we assume that the input signal we are using is an ideal input signal. That means the input signal is like this. It rises from 0 to VDD at time t, 0 time. So for an ideal signal, final point, initial point, final point, and midpoint all will be time t0 because it's an ideal signal. Ideal signal rises and drops instantaneously in 0 time. So this side is 0. So what we are trying to do, we are trying to calculate TPHO, high to low propagation delay. So we have to calculate 50% point of the V out that corresponding time, right? So now, initially the current is constant up to VDD minus VTN, and then current linearly decreases. And we want to, and this is time scale. For the voltage, there is time scale for the current. We are seeing how current through this NMOS network and the voltage at the output node is changing in time. So now if we draw a vertical line from here to here through half VDD point, if we can calculate this time, right, then we get our propagation delay high to low. Because propagation delay high to low is the 50% point of the output minus the 50% point of the input. In this case of ideal input signal, that time t is equal to 0. So for the given scenario, my TPHL is equal to actually t 50% point of the output for an ideal input signal. So now, all we now have to do, calculate this time. So, we know that, let's say, initially this current, let's call it I1 from 0 to VDD minus VTN point. From here to half VDD, that point, let's call the current I2. Initially that I1 is the current flowing through this NMOS. This is in saturation, so we wrote the saturation current equation. The next in I2, the current through NMOS, that is a linear current equation, right? So now let us forget about the transistor and inverter for the time being. We have a capacitor CL. It is holding a voltage V out across it. And while discharging, it is what? It is giving out a current, right? It is discharging. So that capacitor is holding a voltage. When it got a connection to the ground, it will discharge, and a discharging current will come out of that capacitor. Due to the voltage it is holding, that voltage is V out. So, the general basic definition of capacitor. We know that capacitor is epsilon A over D. We also know that capacitor, the current I through any capacitor is what? C dV over dt. These are the two general basic definition of any capacitor. A capacitor will give a current which is proportional to the rate of change of voltage across that capacitor. And the proportionality constant is called capacitance. See. So that is these two are the basic definition of capacitor. You should know this relation. A current, a changing current coming out of the capacitor will be proportional to the rate of change of voltage across that capacitor terminal. And if you want to remove the proportionality sign, if you want to make it equal, the constant of proportionality is called C, the capacitor. So we are going to apply this very basic definition of capacitance current for this scenario. So here, the current that is coming out of the capacitor is a current through an MOS transistor. That loop, there is one current, right? So IN of T, why I put a T? Because this current is changing. Initially it was constant and then it was decreasing. So IN of T, and what is the voltage? V out across the capacitor. So IN of T will be, what is the capacitor? CL. CL dV out over dt. Now the question is, why you put a sign here? Because it is a constantly decreasing current. It's not a rising current. It's a decreasing current because as it is discharging, the current is becoming smaller and smaller. It is being reduced, so it's a negative change of current. So we put a, in case of PMOS, it will be increasing or decreasing charge, right? In increasing charge, here it is decreasing charge. So this rate of change is actually a diminishing quantity. So that's why we put a minus here. So now, let us do some analytic manipulation. Let's put T and T variable on one side and voltage on one side. So if I do, so it will be minus CL dV out equal IN of T dt. Now what we want to see, in this equation, there is one variable is voltage, output voltage, which is constantly decreasing. And there is another variable that is a time variable current, which is constant and gradually decreasing. So both are variable. So to solve this equation, we have to find a way to remove this variable. But in case of V out, we know. We started at VDD and we want to calculate the time when VDD is exactly half. So the limit for this integration is initially at time t0 it is VDD, at time tPHL it will be VDD divided by 2 or 50% point of the output. So for V out, the range we know for which we want to calculate the time. Here we don't know the range yet, but we can write the final point is t0 and the point of interest is tPHL. So it is 0 to tPHL IN of t. Right? This side is a definite integral. It can easily solve. It is because 1 time, so it will be CL VDD divided by 2 on this side. Very simple. But here, IN of T is not one equation. It's two different equations within this range. Initially it is I1, then it is I2. Even in I2 it is not constant. It is continuously going down. So now, there is no straightforward way to solve this side of the integration because there is no definite equation of I of n to solve here. So we have to do an indirect method of estimation. But forget about voltage or transistor, anything. But simple, this is a curve in x and y axis. We are trying to find a certain value on the y axis for a change of x. So now, and we are trying to solve it as an integration. So integration of from 0 to tPHL for this variable is what? is the area under the curve within that limit. So the value of this integration of In of t in time for a limit of 0 to TPHL is nothing but the area of the IN under the IN curve within that limit from T0 to TPHL, right? So that is the integration is the area under the curve. So if we can estimate the area from here to here under IN curve, then we get the value. So we can do two things. Initially, the current is I1, and then in the second part, the current is I2. One way to do it, let's say that the current magnitude is average, I1 plus I2 divided by 2. That is our first assumption. So the area under the curve will be I average times TPHL, because x-axis value is 0 to TPHL, so x-axis value is TPHL. This side, we are just assuming, first it was I1, second it was changing I2. So let us take an average of I1 and I2, so it will be something like that. We'll be leaving something, we'll be adding something extra. So the average, the area of the under the curve will be I average times TPHL, whereas I average is the average of I1 and I2. So basically what we are trying to do, we have the actual point of interest is 0 to TPHL. Initially, this is like this, right? This is I1, here it is I2. But if this side, so if I take the area equal to I average of n times TPHL, what we are doing? I average is I1 plus I2. So basically what we are doing is, we are calculating the area of this rectangle, right? This rectangle includes some additional area, excludes some additional area. So with some margin of error, it is giving me closer number. But then if we want to use I average, then you as the student, you have to first solve for linear equation, solve for the saturation equation, calculate both value, take the average and put them into equation to calculate my TPHL. So the TPHL will be then, because this side is CL VDD divided by 2, this side is I average times TPHL, so TPHL is CL VDD divided by 2 I average. So that is called expression of TPHL based on first assumption, where we are taking, instead of solving for calculating the actual area, we are taking the current as the average of the two. So that is first assumption. The second assumption is, well, between VDD and half VDD, if we assume that, well, the current will remain constant. The change is not that significant, so I average of n is equal to I1. In that case, what we are doing? We are basically taking this area. So we are adding some unnecessary area here. So that will be close, but with some margin of error. So if we do that, then TPHL will be CL VDD divided by 2I1. I1 is saturation current, which is Kn divided by 2, VDD minus VDD square. So then 2 and half will cross each other. Then it will be CL VDD divided by Kn times VDD minus Vtn square. So this is the expression of TPHL based on second assumption. And we want to further simplify the expression. We know that in any given circuit, VDD is always much larger than threshold voltage. So just for simplicity, if we ignore this Vtn term, assume that this VDD minus Vtn is very close to VDD itself, because Vtn is a fraction of VDD. So then if we ignore small Vtn in this equation, what do we have? CL VDD divided by Kn times VDD square. So this VDD and one of the VDD from down will cancel each other. So TPHL will be CL divided by Kn VDD. This is the simplest possible expression of propagation delay. So now we have three simplified expression for propagation delay. First one, we have to calculate both linear and saturation current, take the average of two current and put that in the expression. That is expression based on first assumption, approximation, or we just assume that it is for the linear, the entire duration the current will be equal to saturation current. Then we will be doing this way, second approximation. Or if we can ignore the propagation, the threshold voltage compared to supply, then this will be our third expression. But interestingly, as you can see, in this slide we solve it for TPHL through NMOS. First expression, second expression, third expression. Successively, the expressions are getting simpler, but with higher margin of error, right? But in the next slide, I intentionally put the same three expressions. You don't have to solve this. I just showed you step by step to show how they are related. The parameters and the propagation are related. But in the next slide, I summarized everything for a PMOS transistor. Instead of I average of N, I wrote here I average of P. Because here we are doing it TP low to high. For low to high, it will be PMOS times CL, right? RP CL. Second approximation will be CL VDD instead of Kn in the previous slide. Here I wrote Kn. Kp instead of Vtn, I wrote Vtp magnitude will be same. So now all this expression gives us will give us a simpler way to estimate propagation delay. So now we know that there are two propagation delay, low to high and high to low. So propagation delay Tp is the average of these two propagation delay. And if I take the simplest third expression from here in the previous slide, so propagation delay Tp will be CL divided by 2 VDD times 1 over Kp plus 1 over Km. So now, for us, earlier, we actually mentioned that to make this two propagation delay low to high and high to low symmetrical, we have to make Rp equal to Rn. But Rp and inside that, there is this term Kp and Kn. So if we can make Kp and Kn equal, then they are symmetrical, right? So if we can make Kp equal to Kn, then both will be same value, symmetrical. So, but none of this expression 1, 2 and 3 can be used to calculate actual propagation delay of any logic circuit. Because actual propagation delay or the timing will be dependent on many other parameters. Then what is the utility and value of this expression? You as the designer, this expression will tell you which factor depends on which factor, which parameter. Their dependency. So you as the designer, you know which parameter to fine tune to achieve certain speed, to achieve certain energy efficiency, to achieve certain noise margin, right? So they are showing you the dependency characteristic, which parameter, geometrical and physical parameter, will determine which performance. And if you change one physical parameter, one dimension, how it will affect certain performance to those dependency characteristics, but actual timing can be calculated through real circuit level detailed simulation, which will take care of like hundreds of different factors. So from this expression, what we can conclude? Propagation delay, the average current approximation to estimate the area under the current curve, is an overestimation of actual current, because we are just calculating the area by estimation as a rectangle instead of it's a kind of an exponentially decaying curve. So since we are dividing in the lower side, that average current is always an overestimation of the area, and that overestimation, we are taking larger area and putting it in the denominator. That means the actual value of TPLH will be always significantly higher than HE calculated through any of this propagation delay, because we are successively dividing on the denominator larger and larger value with successive expression to come up with a simple expression. So each approximation will deviate the value of propagation delay further from the actual propagation delay. So it's an underestimation of the propagation delay. But from this expression, what we know? Yes.
So my question is, the expression what we're getting. So in the work, if we are devising something, so CL, DVD, and these are the parameters. If we can change, then we can able to understand what kind of parameter change. My question is, this parameter also related with other parameters inside that we are not calculating. Is it helping? How is it helping us?
Very important observation. So later we'll see that. So let me first explain this, and then you'll be clear. So from this expression, what we see? You want to speed up the circuit. You want to speed up your circuit, so you have to lower this propagation delay. To lower this propagation delay, you have to either lower the capacitance or increase the voltage. How can you lower the capacitance? By sizing down the circuit and transistor, making the circuit smaller, so the parasitic capacitance will be smaller. Or you can increase the supply voltage. If the denominator is larger, this parameter will be smaller. If the delay is smaller, speed will be higher. But the problem is, the power consumption
will go high
of your circuit is equal to current times VDD. As you increase your supply voltage, your power consumption is decreasing. So two of the most important design targets for you will be increased speed by lowering the delay, increased energy efficiency by lowering the power consumption. But just we have seen that lowering the delay requires increasing supply. But if you increase the supply, your power consumption will increase. But you want to lower the delay and lower the power consumption. So in IC design, there is nothing called best design. It's always optimum design. So energy efficiency and speed, the two most important performance parameters, are at conflict. If you want to increase speed, you have to sacrifice energy efficiency.
It's a trade-off.
It's a trade-off. So that's why it's called optimum design. How much power consumption you can tolerate, that is called power budget. So for a given technology size, for a given types of materials and dimension, they will tell you this IC can tolerate maximum 75 watts of heat. So you have to convert, okay, if it can tolerate only 75 watt equivalent of heat, what is the maximum power it can dissipate? 75 watt. So that when you are playing with the higher speed, you have to make sure that you don't cross that power budget. Or if for extremely high speed, like defense application, very high reliable defense application or space application, for them, cost or power probably is not an issue. Efficiency, precision is issue. So they have to come up with another way to dissipate the excessive amount of heat that control circuitry attached to a missile is able to tolerate that temperature. So they have to come up with another way to dissipate that is like liquid cooling, nitrogen cooling, which is very expensive. So that's a trade-off. Is your ultimate goal is to achieve maximum possible speed, no matter how much energy you are consuming, or like a general purpose commercial microprocessor? Well, I have to use my cell phone at least 6-7 hours before charging next time. So I cannot allow that device to consume power beyond certain rate. So then I have to slow it down. Yes.
So my first question is, what's the role of Kp and Kn?
So Kp and Kn, these are device parameters.
Okay.
So from this expression, what we can see, lower Kp, lower Kn will increase the delay. Higher Kp and higher Kn will lower the delay. So Kp and Kn are the device parameters. It is a result of dimension and the material.
Okay.
So Kp and Kn, so from this expression, that's what I was telling. From these expressions, you learn what parameters, physical and device and voltage and signal parameters. There are three types of parameters. Signal, the signal you are applying, VDD. The dimension, geometrical parameters, and the material parameters. These will determine your performances, two performances, speed and energy efficiency. So these are based on device parameters that will, so it is showing the relation. So you, by selecting the appropriate value of Kp and Kn, if your CL and VDD are constant, then you can get certain desirable propagation. Yes.
I have one more question. You said that in space or in rocket, or the space military, they have good amount of power, but they need efficiency and also precision.
Yeah.
But if you talk about efficiency, when you increase the power, the efficiency is...
That was just an example. There are certain defense or space IC applications. Those are extremely high power applications.
Mm-hmm.
Because some of those gadgets are working in hundreds of gigahertz or terahertz level. So that at that frequency, if you just look at the relation,
Okay.
you don't worry about
The power.
because you are sending a satellite signal across the globe. It goes up to outer stellar surface, comes back to another area where probably a group of soldiers or someone else is working, or someone an atmosphere observation where they are monitoring global atmosphere and they're sending signal at terahertz level. So at that level, at extremely high speed level, they want to get the precise data in minimum amount of time. So the speed and the precision of detection is their ultimate goal. They don't worry about power consumption.
Okay.
Because those are specialized applications. Probably in the whole United States there are 5 or 6 major satellite stations where they are monitoring global environment system, right? So that's what I'm saying. Those are specialized type of application where you sacrifice one parameter to achieve the other. On the other hand, when you are talking about an in vivo biomedical sensor, that sensor is probably running at 50 hertz, not even megahertz, just 50 hertz or 60 hertz, synchronizing with your heartbeat. All you need, that pacemaker, now that embedded pacemaker, it has to run with single battery for minimum 10 years. It's ultra low power application. So their ultimate goal is to use it at sub microwatt level, right? So their ultimate goal is energy efficiency. The battery embedded in pacemaker should run 10 years. So speed is not an issue because we are talking about in hertz, not even 100 hertz. So those are extreme examples of specialized application where we sacrifice one parameter for the other. But for general purpose commercial application, day-to-day application, we never be able to achieve highest frequency because then we have to sacrifice power. So it is the optimum. So now let us go back to yes.
So we need to understand what kind of device we're making before.
Oh, yeah. You as the designer, when you work for NVIDIA, it is a graphics CPU, or in AMD, they can tell you it's a graphics CPU or the general purpose CPU. Intel is a general purpose CPU. You know exactly right away what type of application, or if you go to Honeywell, they know they are mainly doing defense IC. So you know the application, you know actually your upper limit for power, your target for speed. Then you start from there. So now, as I mentioned, to make TPHL equal to TPLH, to make it symmetrical, now we are actually subdividing inside Kn and Kp. We have to make Kn equal to Kp. Kn is nothing but Kn primes times W over L of N. Kp is Kp prime times W over L of P. Kn prime and Kp prime, these are material parameter based on the material property. So to make them symmetrical, Kn prime and Kp prime is equal to over this. If we can make them equal, if we make it equal to 1, right, they're equal. So for the condition for AD logic inverter or logic circuit to be symmetrical, Kn should be equal to Kp, or this ratio should be equal to 1. If we can see that condition is satisfied, then it is symmetrical. For symmetrical, upward transition and downward transition will be exactly symmetrical. So the input and output will meet right at the midpoint of VDD. So Vm will be equal to VDD. So now we know the complete definition of a symmetrical inverter. A complete definition of symmetrical inverter means the propagation delay for high to low and propagation delay for low to high will be equal, TPHL equal to TPLH, and also switching threshold voltage Vm is equal to half VDD. So for a symmetrical inverter or symmetrical logic circuits, it will satisfy two conditions. Propagation delay high to low and propagation delay low to high will be equal to each other. Switching threshold voltage will be exactly equal to half VDD. And for this symmetry condition to satisfy, Kn must be equal to Kp. So if you are given any complex math problem with inverter, and if you are asked to find whether it's a symmetrical inverter or not, all you do, first look at all the device parameters and dimension. If this becomes equal to this, then you don't have to solve anything. It's a symmetrical, so my Vn will be half VDD. Yes. So now, the next parameter, timing parameter we mentioned is the transition time, rise time and fall time. These will also determine the speed. So we are going to show a step-by-step process how to estimate the timing, the transition time, rise time and fall time. We are going to do the derivation in a slightly different way, but we can use this technique also to calculate propagation delay. But we will explain it later. But here we are trying to find an expression to calculate rise time and fall time. So rise time and fall time, these are individual signal characteristics. Every input signal and every output signal during the course of operation, sometime it will rise, go from 0 to VDD, sometime it will fall, go from VDD to 0. the time it takes to rise from its initial value to the final value is called rise time. The time it takes to fall from high value to low value is called fall time. So, since in actual circuit, it is very difficult to calculate identify the initial point because it is always oscillating. It is very difficult to identify the final value when it reaches high because it is oscillating. It is a standard practice to calculate the rise time as the time when it is rising. Rise time is the time between 10% point to 90% point. So T rise is T 90% point minus T 10% point. That is the definition of rise time. When the signal is falling, fall time, first it will reach 90% point. At one point it will reach 10% point. So T fall will be T 10% minus T 90%. This will be smaller because signal is falling. So this is fall time. So through this exercise in this slide, we are going to calculate the fall time and then rise time will be opposite. So let us again assume that at time t0, input, we have an ideal input. It changes from 0 to VDD at time t0, we have an ideal step input. So in response, NMOS will be turned on and output will start gradually falling. It will be discharging from initial value VDD to 0. So output initially was VDD. With the increase of with the increase of time, this will continuously discharge. Output will go down slowly. So in this card, we have V out and time. What we are trying to calculate is this time difference. V out at 90% point from V out at 10% point. This is what we are trying to calculate. So if we can calculate this time and this time, 90% point and 10% point, we know the fall time, right? So now we have to solve this curve, xy axis curve, which is a curve of V out in time scale. If we can solve this curve and find these two time points, we have our fall time. So here we are talking about a diminishing voltage across a capacitor, CL. And it is giving out a discharging current. So it's a capacitance current. IN of T will be minus CL dV out over dt, right? Forget about this one. The first part is because dV out of dt is a negative quantity because it is decreasing voltage. So it is minus dV out dt times CL is equal to the current from the capacitor, right? Now, for the time being, let us forget about this capacitor. We have a resistance in the same loop. Across this resistance, in this terminal, what is the voltage that is effective? V out. Current through a resistance is what? Voltage divided by resistance, right? So this IN of T is nothing but this variable voltage V out divided by Rn, right? So in the same loop, same current which is coming out of the capacitor, it is actually passing through the resistor. So if I take the resistance, this current is this voltage divided by resistance, right? But the current out of the capacitor is given by this expression. So they must be equal because it's the same current, it's the same loop. So now let's forget about IN of T. So what we have from this is dV out over V out equal to minus dt over CL times Rn. These two are constant, right? This is the device capacitance, this is the load capacitance. So here, now let's apply the integration. What let's say this is the time. It's a time variable. So we are solving this in this side of integral from time t0, from 0 to t, v out of 0 to v out of t. So it's an indefinite. So we are solving this side from 0 to t. This side is a constant. It's 1 because these two are constant. This is 1 times a constant. So if we solve this equation from 0 to t as a general integration, this is what we have. V out of t is equal to VDD minus VDD times e to the power minus t divided by tau n. This tau n is nothing but RNCL. We just shortened it. Instead of writing RNCL, I use the simpler shorter term. Tau n is equal to NMOS resistance times load capacitance. So by doing the integration from 0 to t here and here, this is the outcome of that integration, where I just wrote RNCL as tau n. Now we can solve this equation because here VDD is a constant, tau is a constant, and this is a variable in time t. How can we solve that? We can solve it very simply. If we take a natural log of this side and natural log of this side, then this exponential term comes here. So t will be equal to tau n times natural log of VDD divided by V out. So I skipped lots of mathematics here. So the final expression is time t, the time in this problem is equal to tau n, which is Rn times Cl, times natural log of VDD over V out. So here, this expression of time t is general expression. We want to calculate 2 times when time t is 90% point of, when V out is at 90% point, and when V out is at 10% point. So T 10% and T 90%. These are the 2 times we want to calculate. So T 10% will be what? VDD divided by 0.1 VDD, right? Because 10%, T 10% is when V out is 10% of VDD. So 10% of VDD is 0.1 VDD. So T 10% is VDD divided by 0.1 VDD. T 90% will be VDD divided by 0.9 VDD. So VDD will cancel. It will be natural log of a constant number, right? So let us call this point as x point, Tx, this point as Ty. 10% point as Ty. So by definition, fall time is Ty minus Tx. 10% point minus 90% point. This one is Tn natural log of VDD divided by 0.1 VDD. This one will be Tn natural log of VDD divided by 0.9 VDD, right? So this is a constant, this is a constant. If you take a natural log, this will be 3.2. This will be 1 or something, but in general, if it will be 2.2. So what do we have? Fall time is 2.2 tau n. Tau n is nothing but Rn times Cl. So from this expression, what we can see, at what rate the signal will fall, faster or slower, it will be determined by this resistance and capacitance. When a capacitance is charging or discharging through a resistance, the multiplication resistance time capacitance is called its RC time constant. It indicates how much time you need to charge or discharge a capacitor through a resistor. So RC time constant, general definition of the time constant is tau. tau is equal to effective resistance times the capacitance. It indicates how much time you need to discharge or charge this capacitance through this resistance. So there is a reason I added tau here. So tau n in this case tells us how faster this capacitance can be discharged through a resistance of NMOS Rn. So if you want to lower the fall time, that is speed up the transition, what do you have to do? You have to have a lower tau n. That means you have to either reduce resistance and reduce capacitance both. How can you reduce both resistance and capacitance in any logic circuit transistor? By sizing them down, by playing with the size. Overall size down, but make sure that widths are wider. Wider the transistor, lower the resistance, right? So that means this relation is giving you a way to determine which parameters you as the designer you have to play with to achieve certain fall time so that the signal falls faster or slower. And as you can see, fall time is linearly proportional to tau n. Tau n is nothing but Rn times Cl, the RC time constant of the pull down network. So tau n is Rn Cl. It is the RC time constant for the pull down network. So without doing the same analysis, because here the mathematical derivation is not the important thing, you all know all those basic integration. So from this slide, further going down, we can, so now tau rise, T rise, for rise time, it will be then a charging signal through RPCM, right? Will be nothing but rise time will be 2.2 tau P. The RC time constant of tau P will be RP CL. So the rise time will be 2.2 tau P. So that's what we are going to mention in the next slide. So we can, I just omitted all the intermediate steps and calculation. I reached the final step. Tau rise time, because signal will rise by being charged through PMOS. So then charging time will be determined by this RP and this capacitance. So the RC time constant of pull up network will determine tau P, and rise time will be 2.2 tau P, where tau P is RP CL. So now, from these two slides, we have now a rough estimation. Again, actual calculation of rise time and fall time must be done through real timing simulation, which is very time consuming and complex simulation. These are rough, very rudimentary expression gives you the idea which parameter is dependent on. So now, if in any given signal, every signal must rise, make a 0 to 1 transition, and then at one point, it will fall again, it will make a 1 to 0 transition. Because otherwise it will not be a binary circuit. Signal has to go from 0 to 1 and 1 to 0. So in one complete clock cycle, any input signal, output signal, whatever signal you are dealing with in binary circuit, you have to give that signal enough time to complete one 0 to 1 transition and one 1 to 0 transition to complete its cycle. Right? So that is called minimum clock period required by any signal. The clock signal should be long enough before you do another operation. You have to give, when you apply a signal, you have to give enough time to that signal to make a complete transition from 0 to 1 and 1 to 0. But in any circuit, your clock signal is what? It's a rectangular pulse. So from here to here, which is called clock period T, this should be long enough for your desired signal to make a 0 to 1 and 1 to 0 transition. So let's say it will rise and the signal doesn't need to stay at high value or low value for a long time. Let's say ideally this time requirement where it must be stable at 1 is going to be 0. But if still your minimum clock period should be long enough to give enough time to raise it, to give enough time to lower it. So that's where it's called minimum clock signal requirement period. T mean for any circuit must be long enough to accommodate the fall time and rise time. Practically, you have to have some additional time because signal cannot just go up and come down. It has to remain stable at 1 and 0 for it to be recognized that it is a 1 or 0. It's like you cannot just open the door and in a fraction of a second you close it before the person can enter, right? So it's like, so you have to give enough time for the signal to be registered. But ideally, if you can enter in this time at rocket speed with infinite speed, yes, you can open and shut down the door in a fraction of a time. You don't need any time to enter. Ideally, this is the minimum clock period you have to provide to the circuit for it to rise and fall properly. Why this parameter is so important? Why we are emphasizing on that ideal minimum clock period? Because you as the designer, you are given a problem, a design problem, and then you asked to find a way, a design solution to achieve 50 gigahertz speed. The very first thing you have to find what, for the given parameter, what is the ceiling, the max frequency is theoretically possible. Your practical frequency will be significantly lower than. So this calculation is giving you the maximum obtainable frequency, theoretically obtainable, the ceiling for any design. If the T minimum is fall time plus rise time, opposite, the reciprocal of T minimum is maximum frequency. So the maximum clock frequency is this, 1 over fall time rise. So now, this simple expression is an overestimation apart from this simple resistance and capacitance value without doing any complex calculation. By using this simple formula, you know what is the theoretical possible maximum frequency. If your material and device parameters and other parameters is telling you that theoretically you can go maximum 5 gigahertz. So if your employer wants a 10 gigahertz from that parameter, it's impossible. You can say it's theoretically impossible. It defies the basic law of science. So you have to know the ceiling, because otherwise, you as the designer, you will be like swimming in the middle of an ocean without knowing actually which are achievable performance parameters. So these simple expressions for both for delay and timing gives us kind of a window where we should limit our design target. Because you know the floor and ceiling, then you know where you can stay. Yes.
Is there like a generally accepted good safety margin to target for? Like in terms of, so if we were hoping to get a 50 gigahertz signal, what should our maximum obtainable frequency look like? Should it be 100 gigahertz?
So basically, even Intel, AMD, NVIDIA, whoever markets their IC, whenever they say it will run at 5 gigahertz, but in hardly in 5% cases you will get 5 gigahertz. 95% case you will get somewhere in the range of maybe 2.5 to 4. because 5 is an optimum condition. In a real circuit operation, you will hardly get an optimum condition. So from the declared performance, it's like Google gigabyte internet. I never get even close to half gigabyte, right? So I think 30-40% is a reasonable target from theoretical, but it depends on what type of application. But as I'm saying, if you are talking about now, there is a company, the symbol is ISRG, Intuitive Surgery, ISRG. They are trying to revolutionize healthcare industry by having robotic surgery and remotely. So there was a joke, okay, that there is a surgeon from India doing a surgery, heart surgery with a patient in America, and there is an internet delay. So if the internet delay even is a fraction of a second, and he needs to do precision cut here, so that delay may basically place the cutting instruction. Instead of cutting the heart, you may actually take out that person's pancreas or something. So the technology is there for remote surgery. And I said this Intuitive Surgery, this company, is trying, or somebody is sitting in Florida, and a doctor from Kansas City is trying to do remote surgery using robots, right? Even if you have the best possible internet service, there will be a fluctuation, right? So still they are struggling with those kind of monitoring. So technology is there. So, but now for rudimentary surgery, they are successfully doing it across the globe, across the continent. But for precision surgery, they are afraid of trying that, open heart or those kind of kidney surgery, and patients probably would not like that. But if we can achieve that level of precision application, probably we can go close to 70, 80, 90%, close to the declared frequency. But practically, if you can even achieve on average 60, 70%, then you are actually on a very good target. On many IC companies' lab, on many top research universities' lab, we have transistors that can switch at 500 gigahertz. But the problem is, transistor is not switching by itself. Achievable frequency of an individual transistor, when you put that transistor inside a circuit with 1 billion additional transistor, all the environmental effect, noise, parasitics from interconnect line and all other packages and all other things, it will actually bring down the real achievable frequency probably less than 10% of what is achievable for individual transistor. Even simple 100 nanometer CMOS transistor, theoretically, you can switch each individual transistor at 50, 60, 70 gigahertz. But practically, we are getting only 2 to 3 gigahertz because that transistor is not operating by itself. It is submerged in an ocean of transistor surrounded by a grid of interconnect line. So those interference will come into play. So we are done with the timing parameter. So we were talking about dynamic behavior of the inverter or CMOS circuit. The dynamic behavior or the transition behavior will determine one of the most important characteristics of integrated circuit, that is the speed or the timing. And the speed or the timing will depend on 2 timing parameters, propagation delay and transition time. Propagation delay is a relative parameter between input and output timing. Transition time is related to each individual input and output signal, how much time it takes to raise it or to lower it. So there can be 2 transition time, rise time and fall time. And we saw that the propagation delay is a function of on resistance and capacitance at the load node. Same as transition time also is a function of on resistance and load capacitance. The dependencies are different, but here, from this expression, we also can calculate another alternative definition of propagation delay. I am not moving to power today. So, signal fall time is Ty minus Tx. T 90% minus T 10%. Now, from this voltage change, what also we can do is Tp high to low. This is the case for an ideal input signal. The way we explain Tp high to low calculation also for an ideal input. So from this card, TPHL is what? Tp at 50% point minus T0. Because input signal 50% point is T0 because it's an ideal signal. At T0 it is going from 0 to VDD. So 50% point, initial point, final point, all will be T0. So TPHL will be T 50% point minus T 0% point. So now, here all we have to do, TPHL is VDD divided by 0.5 VDD at T 50%. Here it will be VDD divided by VDD. Why? Because at 0% at time 0, V out is equal to VDD, right? So it will be tau n, right? Natural log of 0.5, right? 0.5 or 2? 2. Because it is VDD divided by 0.5 VDD, 50% point. It is VDD over VDD because at time 0%. So it is natural log of 2 minus tau n natural log of 1. So what we have here, tau n natural log of 2 minus natural log of 1. Do you know what is the value of natural log of 2 minus natural log of 1? 0.69. So from this expression, what we see an alternative definition of propagation delay. Propagation delay TPHL is 0.69 tau n. If we know propagation delay high to low, it is through NMOS, then this propagation delay low to high can also be, without any further calculation, we can write tau p. Right? So now, the two timing parameters in terms of tau, we can actually write these two here. Now, fall time and rise time. Fall time 2.2 tau n, rise time 2.2 tau p. TPHL, TPLH. This will be 0.69 tau n, 0.69 tau p. So tau p and tau n, this is tau n is RNCL, tau p is RPCL. So in times of RC time constant of pull down network and pull up network, we can estimate both. You can see from here, can you see? We can estimate both transition time and propagation delay. So, and this simple formula, so I want you to just remember, when we are talking about low to high or fall time, both will be determined by tau n. When we are talking about transition time, fall time, multiplying factor is 2.2. Here for propagation delay, multiplying factor is 0.69. When we are talking about rise time and low to high, tau p will determine that value because pull up network will be doing the signal rise and low low to high transition, here factor is 2.2 and 0.69. For transition time, the multiplying factor is 2.2. For propagation delay, the multiplying factor is 0.69. So if you are in the homework and in exam, if you are given a question to solve for rise time and fall time, you don't have to go through all this complex calculation. You have to just calculate what is tau. If you know, if you can calculate tau n and tau p, just put them in this formula, then you get your rise time and fall time as well as propagation delay time. That's all for today. So lecture notes for module 4 and 5 also uploaded in the Blackboard. So let's check them.